Industrial facilities are often treated like well-oiled black boxes. You input power, you extract product, and you assume the design specifications are holding true. But beneath that assumption usually lies massive, unquantified energy waste. To crack open that black box and stop the bleeding, you need a highly structured methodology, the energy audit. This chart outlines the core framework to systematically map an entire facility's energy profile. It is a sequence of overlapping phases. The purpose is to translate raw physical consumption into actionable financial matrices, culminating in that final light bulb icon, costed opportunities for improvement. This entire framework operates on a single, uncompromising axiom: do not estimate when you can calculate, and do not calculate when you can measure. Executing that axiom requires a highly specialized human infrastructure. You need an audit lead to oversee the methodology, field engineers to extract on-site measurements, data analysts to perform the energy balancing, and site liaisons to navigate the operational realities of the plant. This deployment operates with rigorous coordination. A subjective, casual walkthrough checking off lighting fixtures on a clipboard will not yield the data required. True efficiency requires a tactical extraction of live operational data. You cannot optimize a plant by reading its design manuals. The process begins with step 1, defining the audit scope. Before setting foot on the floor, the team determines the required depth of the investigation, whether it's a general survey or a highly detailed investment-grade analysis based on the client's budget. This requires drawing a strict physical and operational boundary. Explicitly defining included buildings, processes, and utilities prevents scope creep and focuses resources. Within that scope, the initial phase requires a desktop analysis to verify the accuracy of utility bills and confirm that the purchased energy tariffs actually suit the facility's consumption profile. Step 2 is understanding the process, and it happens before a single piece of hardware touches a pipe. Auditors map out production schedules, identify load profiles, and account for seasonal variations. They need the full context of the plant's operational constraints so they can gather data without disrupting output. Crucially, this step involves consulting senior management to establish acceptable payback periods and economic guidelines for the final recommendations. If the scope is poorly defined or management's financial criteria are ignored, the resulting engineering data will fail to meet the company's reality. The resulting recommendations will simply collect dust on a shelf. Once the boundary is locked, we reach step 3, data collection. This is the absolute backbone of the entire audit. While reviewing historical utility bills provides a macro view, it is no substitute for physical on-site measurement. Relying on an equipment's nameplate rating or desktop estimations invites massive risk. A motor might be rated for 100 kilowatts, but assuming it constantly draws that exact amount guarantees calculation errors. To extract the ground truth data, the audit team deploys an arsenal of calibrated temporary instrumentation. Armed with these tools, the team measures the plant across all shift variations and daily cycles, capturing reality rather than ideal theoretical operating conditions. They specifically target transient inefficiencies. These are the massive spikes in energy waste that occurs strictly during abnormal periods, like machine startups and process shutdowns. A paper audit inherently creates a false baseline. Only high-fidelity physical measurement can expose the expensive realities of how a plant actually operates. On the plant floor, the first major target is typically the largest energy consumer, 3-phase electric motor systems. This analyzer display shows critical electrical supply parameters, capturing active power and issues like total harmonic distortion. These wave fluctuations map directly to equipment performance. Just a 1% voltage imbalance drastically derates motor efficiency, causes overheating, and triggers utility penalty charges. From the electrical panels, the audit moves to the physical distribution of HVAC, chilled water, and process fluids. This ultrasonic flow meter is clamped directly onto a pipe, allowing engineers to measure volumetric flow rates without shutting down critical cooling lines. The digital readout provides real-time velocity and totalized flow data, absolutely critical for calculating total heat transfer rates and verifying chiller performance. These non-intrusive diagnostic instruments offer the only viable method to accurately map true loads on live, moving industrial processes. Next, the focus shifts to some of the highest margin targets for energy recovery: thermal and steam systems. This thermal imaging readout exposes exactly where heat is escaping. Thermographic surveys reveal invisible thermal bridging, missing pipe insulation, and even failing mechanical bearings long before they cause unplanned downtime. Similarly, compressed air is often the most expensive utility in a facility. Finding microscopic, inaudible air leaks that steadily drain capital requires specialized ultrasonic leak detectors. We then trace the thermal energy back to its generation source, the combustion boiler. This schematic illustrates the deployment of a flue gas analyzer. By probing the stack to measure oxygen and carbon monoxide levels, engineers can perfectly optimize the burner's air-to-fuel ratio, immediately reducing flue gas losses. By making the invisible physics of heat and gas visible, these tools turn unknown, untracked waste into precise, actionable data points. Once the data is gathered, we reach step 4, identifying existing performance by establishing strict current benchmarks. Raw instrument readings mean very little on their own. To be useful to management, that energy data must be normalized against production variables. This dashboard tracks specific energy consumption, measuring the exact energy required to produce a single unit of output, to provide a definitive benchmark. By analyzing the load factor, auditors can immediately pinpoint poor utilization, unnecessary standby loads, and the cost of running equipment idle. This data culminates in a facility-wide energy balance, visualized as a Sankey diagram. Entering energy branches out, mapping useful work against measured losses. This forces total accountability. Total energy inputs on the left must perfectly equal the useful outputs plus identified losses on the right. This mathematical model is the vital bridge. It converts isolated, localized gauge readings into a unified, irrefutable map of the entire plant. With the baseline mapped, Step 5 identifies the specific opportunities to eliminate those measured losses. These targeted solutions are defined as energy conservation measures, or ECMs. To make them actionable, ECMs are categorized into 3 tiers for the client. First, no or low-cost operational tweaks, like optimizing set points. Next, medium-cost upgrades, like installing variable speed drives. And finally, capital investment measures, like major boiler replacements. Step 6 finalizes the process with the delivery of the audit report and the implementation roadmap. This framework shows the rigorous evaluation criteria applied to every energy conservation measure before reaching a CFO's desk. The technical merit of an engineering solution cannot stand alone. It must be weighed directly against its financial payback period and potential implementation risk to the facility. Identifying a thermodynamic inefficiency is intellectually interesting, but it is practically useless unless it is packaged into a costed, risk-assessed, and phased delivery plan. The process moves strictly from scoping the physical boundaries to extracting raw thermodynamic data on the plant floor to delivering an executive financial roadmap. Assumption and estimation remain the greatest enemies of industrial efficiency. Precision physical measurement is the only path to true optimization. An energy audit operates as the ultimate translation layer between the immutable laws of physics and corporate financial strategy.